Hi, my name is Timothy Oxley, and I have built a railway signalling system simulator to explore the benefits of communication-based train control. When a suburban rail network has reached its capacity in terms of the number of passengers that it can move during a peak period, a railway operator can invest in a network to improve throughput. They may invest by adding more tracks, building longer trains, or by upgrading the signalling system from fixed block to CBTC. All options increase the number of passengers which can be transported simultaneously. This report focuses on the benefits of upgrading to CBTC, which enables trains to operate at closer distances without the risk of collisions. It is also the least expensive option for an operator to invest in. To explore the possible improved performance of a CBTC system against fixed block or against other alternative upgrades, a simulator has been created which emulates the movement of trains that would occur on a specific railway line, as defined by the user. This allows the controlling influence of either signalling system to be compared and for improvements to be quantified. To be of use to a rail operator, this simulation must consider a variety of physical factors to produce realistic results, such as the dynamics of different trains, constraints when setting timetables, and the influence of delays caused by passengers. Through the input of absolute data sources and mathematical models, observations have been drawn considering the impact of improvements to the experience of passengers using the service. This tool also allows operators to determine how they could adjust timetables to improve the service delivered. After emulating many of the possible scenarios using the simulator, it has been concluded that upgrading to a CBTC signalling system can result in reductions in delays of up to 43% and the ability to transport up to 33% more passengers simultaneously. This is a significantly stronger improvement compared with purchasing longer trains, which can only carry 17% more passengers. CBTC also requires minimal investment in new infrastructure when compared to the cost of building additional tracks. Fixed block versus CBTC. The current signalling system in use utilises a principle known as fixed block, which divides a track into sections with a defined start and end point. Circuits which sense the presence of trains within a block feed the logic controllers of the signalling system, which do not let a train enter a block unless if the track circuits have proven it to be vacant of any other trains. At that point, the signal at the beginning of the block will turn from red to green, allowing a driver to proceed into the block. To ensure that safe braking distances exist between trains at all times, a buffer of at least one empty block is enforced by the signalling system. As the length of each block is determined by the braking distance of a train operating at full speed, this results in trains being held further apart than they could be by the staggered sequence of signals turning green between leading and trailing trains. A new signalling system called Communications-Based Train Control, otherwise known as CBTC, utilises a principle known as moving block. This replaces fixed track circuits with the continuous absolute knowledge of a train's location. It does this by continuously measuring a train's odometry and communicating it to wayside receivers. Wheel sensors placed at regular intervals also serve as a reference point when a train passes, reducing any errors in measured odometry that may accumulate. This allows signals to be removed from the field and placed into the driver's cab, constantly providing feedback to allow finer control and reducing the buffer distance required between trains. A further advancement to CBTC is automatic train control, which reduces buffer distances even further because the system no longer needs to account for a human's reaction time to a changing signal. While CBTC systems improve the performance of all rail lines, the extent of improvements is dependent on the layout, demand, and operational constraints of the line in question. This is why, prior to investing in any upgrades, it is important to simulate and compare the performance of both systems on an existing line to understand how they behave differently. But how can a railway line and the signalling system controlling it be effectively simulated? By breaking down and simulating each component that interacts with the performance of a system, the controls and resulting movements of trains can be emulated in real time. The components are the layout of the rail line, the movement of trains, the location and status of signals, the timetable, and the influence of passenger demand. The basic structure of the simulation can be represented by this programmable user interface. Each component of this interface interacts to depict the flow of code used in the simulation. By fitting these components together, either signalling system can be modelled and the influence of any changes to the system can be compared. Project development. Mapping the railway line. The locations along the railway line is stored in downline data, where down represents the direction of travel away from the city and up would represent the line travelling towards the city. This has been achieved by analysing the signalling area designs provided by the Caulfield to Dandenong Level Crossing Removal Project. It includes the locations of all signals and all station platforms. Train operating limits. Each train type used in the simulation has different acceleration and braking rates, as well as different allowable top speeds along the line. These operating limits are stored within the rolling stock data matrix, yet this doesn't account for how drivers may control their trains. Just like how every one of us drives our car differently, every train driver will also control their train with some degree of variation. Therefore, the performance of each train is set within the getTrains function, using the operating limits defined by the values set in rolling stock data. It's worth noting that a CBTC system using automatic train operation would not perform with this variation in control. Once CBTC is added to the simulation, the getTrains function no longer produces any variation between trains. Train movement. The simulator operates in a continuous loop using the movements function for the period that the user sets. For each train, the movements function searches for the next obstacle along the line. Based on the obstacle's location and the speed of the train, the function will choose to speed up if it has not yet reached top speed, coast if it has already reached top speed, or slow down if approaching a signal or a station. Every time that a train arrives at a station, it must dwell there for a period long enough for passengers to board and depart. The instantaneous location of each train is also stored so that it can be used by other functions and to produce results. Updating signals. For a fixed block network, the location of both the front and rear of each train is used by the blocks function to determine which blocks are occupied. This information is then used to update the status of each signal in the line data matrix. As this update occurs every second, and the location of trains is updated every second by the movements function, trains are instantly able to react to the feedback of signals changing status, as they would in real time. Moving block. This feedback loop is the same for a moving blocks function, except the status of signals never changes. Instead, the locations of signals move with the location of trains. The moving blocks function places two signals behind every train. One is red to completely stop trains from colliding with the one ahead. The other is yellow to force trains to reduce to medium speed if they come within a certain distance of the train ahead. Enforcing this medium speed buffer can prevent a train from stopping unnecessarily between stations, as it allows the leading train to regain headway before bringing the trailing train to a stop. Running to a timetable. An existing timetable can be used by the simulation to see how well either signalling system adheres to it. The current timetable has been extracted from online sources for both the suburban trains, operated by Metro Trains Melbourne, and the regional trains, operated by V-Line. Using this timetable, the entry of trains into the simulation can be fed into the getTrains function. Every time that a train arrives at a station, the dwell period estimator uses a timetable to determine how long the train should wait at the platform so that it does not leave earlier than its timetable departure. If it is running late, any delays are recorded as accumulated for that train, though a minimum dwell period must still occur at each station for passengers to board and depart, even if the train is running late. Simulating passengers. Modelling the movement of passengers is important because timetables need to be generated to meet passenger demand. Demand is specific to each station, depending on the population density of the area. Patronage for each station has been sourced from Public Transport Victoria, allowing the relative use of each station to be stored in the station data matrix. This data doesn't differentiate between passengers travelling in the up and down directions. It also doesn't differentiate between the likelihood of a station being the source of passengers or the destination. To make this distinction for trains travelling towards the city, patronage has been divided by using a formula. It dictates that a station is more likely to be a source of passengers the further away it is from the city. Conversely, a station is more likely to be a destination the closer it is to the city. This does not account for the variation in passenger demand that is observed across a morning or an afternoon peak. To simulate this trend, the probability of passengers arriving at each station is scaled within the passengers arriving at stations function. This emulates the random yet determinate nature that passengers arrive at stations to board trains. Logically, passengers can only travel to and from platforms while the train is stopped. During the passenger movements function, this transfer takes place, allowing the number of passengers that board each train to be recorded. Simulating passenger-induced delays. The volume of passengers transferring between a platform and a train at each stop influences how long a train is required to be stationary at the platform. By modelling this relationship in the passenger delay generator, the resulting dwell periods are transferred to the dwell period determination function. Other delays can be influenced by the activities of the train driver, such as a need to go to the bathroom or to assist disabled passengers to board and depart trains. These are simulated to occur at random for each station stop. Results. Due to the relationship that exists between the number of passengers boarding each train and the extent of delays incurred, it can be immediately justified that it is desirable to maintain the shortest possible headways between trains stopping at platforms, especially during peak demand. This is because a platform that is vacant for a longer period will accumulate more passengers, which will increase delays to the train when it arrives. The increased delay will lengthen the period that passengers can accumulate at the next platform, resulting in a snowballing effect until the train is fully loaded. As a CBTC system has the ability to operate with shorter headways and fixed block, the reduction in delays should be apparent in the results of simulations. All simulations have been conducted using 50 iterations of each scenario to iron out the noise between results. Improved train dynamics. The performance of either system can be improved simply by using trains that can accelerate and brake harder. This allows journey times between stations to be reduced. If a train arrives early enough to a crowded platform, it may not accumulate any delays, as a departure will still take place after all passengers have boarded. Despite this, a CBTC system consistently performs with 43% less delays across all scenarios tested when operating on the same timetable as the fixed block simulation. Reducing medium speed buffer distance. In order to carry more passengers, the headway between trains must be reduced. At a certain point, the medium speed buffer distance prevents headways from being reduced without sustaining significant delays. A CBTC system can reduce headways from 180 seconds to 120 seconds, which improves passenger carrying capacity by 33%, but still results in a similar quantity of delays being incurred as a fixed block system. Reducing this buffer distance can result in significantly less delays, though may lead to more unplanned stops between stations, which results in a degraded passenger experience. Using longer trains. An alternative to investing in CBTC is to use longer trains, which can carry more passengers. Increasing the length from 6 cars to 7 cars improves capacity by 17%, yet only reduces delays by 4% when operating on a fixed block system. Increasing passenger demand. Scheduling trains closer together using CBTC increases the passenger carrying capacity, but also allows delays to propagate more easily between trains. Against a steadily increasing passenger demand, CBTC is able to perform with less delays than a fixed block system, indicating that it can effectively cater for future growth. Conclusion. Through the use of a detailed simulator, the ability for a CBTC system to operate trains with reduced headways along a Dandenong corridor will result in a vastly improved passenger experience. Not only will the line be capable of transporting up to 33% more passengers simultaneously, this will also result in less passengers travelling on each train and less delays occurring. The benefits to this system outweigh the improvements that will come from building longer trains, indicating that it is the first improvement worth pursuing by rail operators. These outcomes have been produced from the focus scenario simulated. Though using this tool, it is possible to test a range of scenarios on any rail line to determine the resulting change in performance. Thank you.